Just so this one, first thing, you're given in the question, you have to figure out this molecule. You're given the m+1 ratio, right? So what information can you extract from that? It's going to be the number of carbon atoms, right? The formula is 100 over 1.1 into m+1, which is this one. It's 3.35, and divided by the other one, which is 43, the m peak, which is 43.3, right? Is that clear? Munya, can you do the math and tell me what is the total number of carbon atoms?
Okay. What are the figures then?
Okay, just a second.
Okay, thank you.
This one, 3.35 divided by 43.3.
Seven.
So we've got 7 carbon atoms. So that's kind of a big number, because if you have a lot of carbon atoms, it's harder, because now there's going to be a lot of combinations, and it's going to be harder to figure out what the molecule is. So this one is a slightly more difficult question. So I said, what do you get from the mm+2 peak? That's the other information that's provided. He's saying what element do you extract from that? So what is the ratio mm+2? What is 14? So you just have an mm+2 ratio, and the ratio is this is 14.1 and this is 43.3, right? So that's approximately or roughly 3:1, right? So when you have an mm+1 ratio, and that's coming out to be, where's the chlorine part? This one, right? That when you have an mm+2 ratio and the ratio is 3:1, that indicates that it's got 1 Cl. Is that clear? You've got 1 Cl, right? So Munir, is this clear?
Yes, sir.
Okay, then the next thing is the molecular ion peak, the mass spectrum of the highest mass. It's 142, 143, and 144. That's because of the isotopes. So I'm going to take the lighter one, that's 142. So I know that whatever this molecule is, it's got 7 carbon atoms, it's got 1 Cl, and its total mass is coming out to be 142, right? So, this is some information that I have. Then they show me the NMR spectrum for this. So what do you think is missing? How do you get to 142? What's 7 carbons? 7 carbons is 12 into 7, right? And there is 1 Cl, so that's 1 into 35. Remember, I'm talking about the M peak. The M peak is the lighter. It's made due to the lighter isotopes. So what is this? Can you total that and subtract it from 142?
Sodium 90.
What is this? What is this total? Like when you subtract it from 142, what do you get?
23.
You got.
Sorry. Yeah, 23.
Okay, you're getting 23, right? So there's a 23 missing, right?
Yeah.
Now the NMR spectrum is given. Remember, what did I tell you about the heights of the NMR spectrum? What information do you get from the height of the NMR spectrum? That where's the NMR spectrum? For the NMR spectrum, I told you that it gives you, must have written it somewhere. So I told you that it gives you this thing. It gives you the number of chemical environments. It's also giving you the number of protons in those chemical environments. So you've got 4 hydrogens over here, right? You've got 2 hydrogens in this environment, right? And you've got 1 hydrogen in a different environment. Okay, is that clear? So that's a total of 7 hydrogens. So I now know this thing is C7. There's 1 Cl, and there are 7 hydrogens as well. So if I remove 7 hydrogens, I'm left with 16, right? So I'm still not reaching 142. So 16 must be oxygen, because if I include the oxygen, the hydrogens as well, then this 16 must be an oxygen atom. Is that clear? So my formula now is C7. There is one Cl and there are 7 hydrogens, because that's clearly the NMR spectrum clearly shows the distribution. And it's got one oxygen. That is going to give me 142. Is that clear? So now the tough part. Remember, there are 3 chemical environments. So the hydrogen protons are going to be distributed in 3 chemical environments. Now, the first hint that you should have is, when is the carbon and hydrogen ratio so low? When do you have a very low ratio of carbon and hydrogen? I mean, I'll just add an extra tip as, so some useful tip, that is that if the carbon and hydrogen ratio is close to 1:1, that would kind of indicate that it would indicate the presence of benzene. Right? Is that clear? Because usually the number of hydrogens are double the number of carbon atoms in alkenes and in alkanes as well, and pretty much in all organic compounds. But in benzene, it's like a very low ratio. So I've got a benzene. I've got so I'm going to draw the structures. It's probably going to be, so that is 6 carbon atoms out of the way, right? So what am I left with? I'm left with 1 carbon, right? And I'm left with 1 Cl, and I'm left with 1 oxygen, and I'm left with 7 hydrogens, right? So the 6 carbons can be accounted for in the benzene ring. So so I've got a Cl, so maybe there's a Cl, and I've got an O. I've got another carbon as well, so maybe there's a carbon attached to it, and I've got an O as well. So probably there is a CH3, and then there is an OH, right? And then I have 4 hydrogens. So that's just one random molecule that I've drawn. So that kind of sums up one version of the molecule. It's just a hunch. It's just a rough guess. Does it have 3 environments? It does have 3 environments. If you look carefully, it's got 3 exact environments, because there's an OH hydrogen, there is this CH2 hydrogen, and there are 4 hydrogens that belong to benzene. Is that clear? So the environment kind of matches this. But it kind of matches it.
Can you review the previous parts of the questions so I can link?
The previous part was simple. Okay, you had the MM+1 peak. Those, what do you get out? What information do you get out of that? You figure out the number of carbon atoms, right? Clear?
Okay.
Then you had the MM+2 ratio, and he told you what is the M+2 tell you. So MM+2 ratio is given as it's almost 3:1, right? 43:14. So when you have an MM+2 ratio of 3:1, that indicates that there's 1 Cl. Is that clear?
Yes.
Just you figured out that the molecule has 7 carbon atoms. It's got 1 Cl. And they told us the molecular ion peak as well. They said that it was coming at, the peak was 142, 143, and 144. So the lightest molecular ion peak was 142. So I know the MR as well. I know that if I use the lighter isotopes, the mass should come out to be 142, right? So there's 23 missing. When I looked at the NMR spectrum, they gave us the height of the peaks as well. That there are 3 chemical environments. There are 4 hydrogens in this environment. There are 2 hydrogens in this environment, and there's 1 in this environment. So you have a total of how many hydrogen protons? You've got 7 hydrogens, right? Is that clear?
Yes.
So if I add all of them up, I've got 7 carbons, I've got 1 Cl, and I've got 7 hydrogens seen over here. So to make it up to 142, there should be 160. There should be something that has a mass of 16. So that must be an oxygen atom. Is that clear?
Yes, sir.
So now, this is what I've figured out. This is the structure of the molecule. Then I told you that when you have a very low carbon hydrogen ratio, that indicates that there is a benzene. Because in pretty much all organic molecules, the carbon and hydrogen ratio is 1:2 or more than that. Is that clear? So I saw 7 carbons, I saw 7 hydrogens. My hunch was that there must be a benzene in the structure. Is that clear?
Yes, sir.
So if I put a benzene over here, I put a Cl, I just drew one random molecule. I put a Cl over here. I put an oxygen over here. I had one extra carbon, so I put it over there. Now there would be other versions of this molecule as well. So the other versions would be K. I mean, the benzene is there, right? So maybe there's a Cl, there's an OH over here, right? And this one has 3 H's, right? And this one has, the benzene has 4 hydrogens, right? No, just 3. This is not going to be the correct structure because there are 3 hydrogen protons in the same environment. Is that clear? So
Yes.
So that's not possible because we would have gotten a peak with a relative ratio of 3, which we don't have over here. So we don't have 3 hydrogens in the same environment. Is that clear? I've rejected this one. This one exactly matches this one. This one is 4 hydrogens in the same environment. So that's this one. 2 hydrogens in the same environment, CH2. And then there's an OH hydrogen, that's this one. So then there could be other arrangements as well. Let's try and draw some other isomers that fit this enema spectrum. So maybe you got an OH here. And the 7th carbon atom had a Cl over here. And then there were 4 hydrogens. So that's another example. So this one is, how many environments does this have? It's going to have OH, that's CH2. Or it could have the 4 hydrogens on benzene, right? So this kind of matches this one as well. So there are basically two structures that are matching this. Not really sure how I can arrange it differently. So which one is the correct structure? So the correct structure is this point clear that the 4, 2, and 1, 3 environments, 4 hydrogens, 2 hydrogens in a different environment, 1 in a different environment, 4 hydrogens in one environment, 1 in a different environment, and there's 2 in the same environment. So the spectrum kind of matches both of them. Is that clear?
Yes, sir.
So the final thing is, which one is the correct option? So for that, you'll open the data booklet, sorry. So we'll have a look at the NMR values now. So the NMR values would be just one second, everything. That's this one. So we have to look at the NMR value. So one of them, like this one, you've got 2 candidates, either this one. So one of them is a normal alcohol, the other one is a phenol alcohol, right? So the OH peak must be this one because there's only one single peak. OH has only one proton, right? So it must be, I mean, this peak over here must be the OH peak. So we've got 2 options, it's either a phenol or it's an alcohol. So if I open the data booklet and look at the NMR spectrum.
Okay.
So I've got a phenol. The phenol is between 4.5 and 7, right? So if I go back and if I focus on the phenol part, the OH is not, it's not at 4.5 to 7, right? So definitely not a phenol.
Alcohol.
So that would eliminate this possibility as well, because it's not phenol. Is that clear? But it
Yes,
can
sir.
but it can be an alcohol, because the alcohol peak, where's the alcohol? The OH peak, this one. It's at 0.5 to 6. So it does fit that range. I mean, it can be 0.5 to 6. So this one can be alcohol. That makes sense, but it can definitely not be a phenol. So which is why I've eliminated this one. So this is the correct option, this one over here. Is that clear?
Yes, sir.
So Munir, is this clear?
Yes, sir.
Okay, the next one is you've got just hold on a second. Acha. So the next one is you have to draw the structure. It's a 7-mark question, so you have to explain everything. So moving to the next part, you can, I mean, check the market scheme as well, how this is answered. I mean, the way it's going to be answered is you're going to state this, that the chemical shift value at 2 point, whatever this number is, 2.2, represents an OH, which is part of an alcohol. The chemical shift at 7 represents 4 hydrogens in the benzene ring, right? And the chemical shift at this 2H, the CH2, this is the CH2. So it represents a CH2. So you combine them together, you give the structure. The 7 marks are for the total thing. So I think this last part would be probably for 3 or 4 marks. So make sure you code those values and then you describe them what the structure is. Now this one. Suggest one difference in the fragmentation pattern and the mass spectra of these compounds. So remember, when you do mass spectrum, fragmentation pattern gives you hints about what type of structure is present. So if you look at these 2 molecules, this one over here will give you a peak at 15, which would be a CH3 plus 1 fragment. I mean, the molecule could break at this point, and it can form a CH3 plus 1 fragment. This one over here can never form a CH3 plus 1 fragment. So no detections or fragments at 15. Is that clear? Like if I break this piece, that's 14. So, and if I take some other piece, there would be another carbon that would be added to it. So it would be, the mass would be a lot, much higher than 15. Is that clear?
Yes, sir.
So
yes.
Sorry,
sir. Can you come again, please? I didn't catch that one.
Yeah, I'm just saying what happens in mass spectrum, right? What happens in mass spectrum is that, where's mass spectrum? So what happened in mass spectrum was that you'll take a molecule and so let's say this one, not this one. So what will happen is that you'll take a molecule and you'll bombard it with electrons, right? And it will turn into an ion. It will turn into an ion, or it would break into small pieces, right? So small pieces will be detected, right?
Yeah.
So these small pieces are part of the bigger piece, right? The bigger molecule, right?
Yes, sir.
So when you do mass spectrum of these 2 molecules,
yeah,
there's a possibility that a fragment with a mass of 15 can be detected in propene, because the molecule will break into at this point and it will form a CH3 plus 1 fragment. Is that clear?
Okay. Yeah, I'm with you.
Okay, but this one will never actually give you it will never give you 15. Like if you break any small piece of the molecule, it will never come out to be 15. So that's one difference, right? No, sorry, for fragmentation pattern, they were just looking for one difference. So we've told that difference, right? And for NMR spectrum, they're looking for two differences. So NMR spectrum is about the hydrogen protons, right? So,
Yes.
so can you tell me how many different peaks, how many different hydrogen environments are there in this one?
Just one.
Just one, because they're all exactly the same. So this one will have exactly only one peak in the, and no splitting, right? What about this other one? How many different environments for this one?
3, I guess. 3.
Okay, so it's going to be 3 because these hydrogens are a different environment. This one is different. This one is different. So this one is going to have 3 peaks, and there would be splitting. That is because there would be neighboring hydrogen protons resonating at a different frequency. So they would interfere with this hydrogen. Is that clear?
Yes,
Yes, sir.
So then this one. I mean, the first hunch, if you look at an NMR spectrum, if it's 2 given, that's 2 hydrogen protons. That's probably going to be CH2. This is 3 hydrogens, that's probably going to be CH3, right? Because, I mean, that's how 3 hydrogens could be in the same environment. This one is probably CH3 as well, right? Like the 3 hydrogens are in the same environment, so it's probably going to be CH3. So the MM+1 peak is given. So can you tell me the number of carbon atoms if the MM+1, what is it going to be? 100 over 1.1 into 0.22 divided by 5.1, right? So what do we get for this?
4.
So we get 4 carbon atoms, right? So this one has 4 carbon atoms. And they've told us the M peak, it's 88. Now, based on this, I know that it's got 2 hydrogens, 3 hydrogens, and 3. So that would be C4. How many hydrogens? That's 8, right?
Yeah.
And the total should be equal to 88, right? I mean, that's given over. It should be 88, right? So what is missing here? What's C4? That's 12 into 4. That's 48 plus 8. That's 56. So what's missing? 32 is missing.
32 is missing. Yes.
So what's your hunch? 32 must be two oxygens, right?
2 oxygens, yeah.
So that must be 2 oxygens. Did they tell anywhere that they didn't tell anything, but probably going to be 2 oxygens, right? I said, so I know. So the first thing is what I know about the NMR spectrum is that this is CH2, this is CH3, and this is CH3. Now look at the splitting. This is a quadruplet peak, right? When you get a quadruplet peak, when the neighboring carbon has how many hydrogens?
3.
That means the neighboring carbon atom has 3 hydrogens. So neighbor is probably going to be CH3, right?
Yeah.
I said this one has no splitting. So how many hydrogens on the neighboring carbon atom?
No hydrogens.
You can no hydrogens because N+1. If the neighbor has 0 hydrogens, you'll have 1 peak. So neighboring H has no H atoms. This one is a triplet peak. So how many neighboring hydrogens? That's going to be
2.
So the neighbor is probably going to be CH2, right? So that's one thing. So I know that right next to CH2 there must be a CH3. And I know that right next to CH3 there must be a CH2. So that kind of solves part of the structure. That I know that the CH3 and CH2 are together, right? Is that clear? That's how the splitting would work. Is that clear? Baza clear, Munir?
Yes, sir.
Okay, the other thing is that you've got another CH3. Remember, you have 4 carbon atoms. You've got another CH3. and no splitting. So that's a singlet. So that's kind of far away from all these other hydrogens. So what are you left with? You're left with one carbon and two oxygens. So what could be one carbon and two oxygens? That must be an ester.
Yeah.
It must be an ester. It could be one carbon and two oxygens, right?
Yeah.
Because I have to, this one is a singlet, so I have to keep it far away from the other hydrogens, right? Is that clear? But this is, there are two ways, there are two arrangements for this. The other possible arrangement that you could have is, I mean, you could have CH3, CH2, and the CH3 is far away because it's a singlet. And the ester could be the other way around. It could be O and serial bond O. So is that clear that you can have two possible arrangements, right?
Yes, sir.
I said, now what I need to know is which one is the correct one out of the two. So I'm going to look at the values. This one was for the CH3, right? And sorry, let's look at the singlet. Singlet is this one. So it's resonating at somewhere around 2. So if I open the data booklet, when does it resonate around 2? When it's right next to a carbon which is making a double bond O. Is that clear?
Yes.
Oh, yeah.
If it was next to a carbon that was making a single, was bonded to a single oxygen, that would resonate at somewhere around 3.2 to 4. So in our case, it's 2. So we know that this singlet is right next to serial bond O because it's around 2, right? So it's going to be this one. That's not going to be correct because our singlet peak at the chemical shift around 2 indicates that it's right next to serial bond O. Is that clear?
Yes, sir.
So this one over here is the structure of the molecule, which we have figured out. I said, then
Sir, I don't get it. I mean, you have C double bond O. From both sides, we're getting an alkyl chain.
Because a singlet was CH3, right?
Achha, okay, yes.
So in both cases, the singlet peak is this one. I mean, not the other one. Okay. I mean,
yeah, okay.
I mean, this one is going to be the quadruplet. And this one is going to be my triplet peak, which is going to be the same in the other one as well. But I'm focusing on the singlet. The singlet will tell me which CH3 is it. Is it right next to an oxygen or is it right next to a double bond O? Since it was 2, I know that it's right next to a double bond O based on the data booklet. Is that part clear?
Yes, sir.
So here's another one, probably an easy one. He's saying that the mass spectrum MM+1, can you tell me the number of carbon atoms? It's 100 over 1.1 into 0.2 divided by 5.9, right? So how many carbons do we get for this?
3.
It's a 3 carbon atom molecule. And then there's an M+2 which has a similar height to the M. What does that indicate?
Benzene?
No, not benzene. When you had similar heights. Bromine. When the M+2 had
Achha,
similar.
yeah, okay.
That was because the probability of getting 79 and 81 was exactly the same. So this one indicates that there is one bromine exactly, right? So far I know that I've got 3 carbon atoms, I've got 1 bromine. So, and did they tell us the MR? They didn't. So how many atoms we figured that out? I said they've given us the hydrogens as well, 6 hydrogens and 1 in this one. So that's a total of 7 hydrogens. So that is the NMR spectrum is saying that there are 7. So that's my molecule now. And I need to figure out the structure. So I know that it's 3 carbon atoms,
Sir,
right?
for bromine, isn't it supposed to be like M+2 peak and M peak?
It's the M+2 and M.
Oh yeah. Okay.
They have similar height. Achha, so I know that this one, so I can draw isomers, right? It's either the Br is at the end. How many chemical environments would this have? If the 7 hydrogens and 3 carbons and the Br is right at the end. So how many environments?
1, 2, 3.
So it's going to be 3. So that's clearly the wrong one, right?
Mm.
And there are just 2 isomers. The other one is that the Br is in the middle, right?
Yeah.
So how many hydrogen environments in this case?
2.
Because the 6 hydrogens at the ends are exactly the same. So that's this one.
Mhm.
And there's 1 H. Because of the H, this one is going to be a doublet.
Yeah.
Because the neighboring carbon atom has 1 H. I mean, the neighboring carbon atom over here also has 1 H. And because of the neighboring carbon atom, this H is going to be a multiplet. So that's 1 H, that's a multiplet. So that's the answer. This one is the correct one. Is that clear?
Yes, sir.
Yes, sir.
So similarly, we have, remember, X-rays are not in your course. You're saying 2 molecules, propanol and propanol, have the same molecular formula. Draw the displayed formula of each compound. Explain briefly how NMR spectroscopy can distinguish between the 2 structures. So propanol is this one. So how many peaks in this one?
This 1, 2, 3. 3. The first one, 3.
Okay, so it's going to have 3 peaks, right? And this one is going to have 1 peak, right?
Yeah, that one, 1 peak.
And there's going to be a triplet peak. I mean, there's going to be splitting in this. This one is going to be a single peak, no splitting.
Yeah.
And there would be splitting in that case. That's it.
Okay.
Okay, this one is he's saying 2 NMR spectra 1 and 2 are obtained before and after an alcohol Y was oxidized to give. So alcohol Y is getting oxidized, right? So alcohol Y is oxidized. What can be the possible products when alcohol Y is oxidized? I mean, this is, I think, the alcohol Y. And this is the compound Z that is formed after oxidation. So alcohol, whether it's primary, secondary, or tertiary, how many different products are possible when an alcohol gets oxidized? What will happen? You'll get
carboxylic acid or a ketone.
So you're going to get a carboxylic acid.
Mm.
So that's one option. You can get a ketone, or you
An
can also,
aldehyde.
or you can get an aldehyde, right?
Mm.
So which of these products do you think can have a single peak? Can a carboxylic acid ever have a single peak? Like any carboxylic acid? Like if I make this smallest carboxylic acid, methanoic acid, will it have a single peak?
The OH is there, so yes.
Yeah.
But there's an H as well, so there are going to be 2 different peaks, right?
Yeah. Yes, exactly.
So there's going to be 2 different peaks. Even if you take ethanoic acid, it's going to have. I mean, ethanoic acid will also have lots of peaks, like 2 different peaks, right?
Yeah.
So I don't think a carboxylic acid is possible because a carboxylic acid is never going to have a single peak. Right? Is that clear?
Yes, sir.
Yes.
So I'm ruling out carboxylic acid. What about a ketone? Can a ketone have a single peak?
Ketone.
Like,
Yeah,
do
could
you,
have.
which ketone specifically has just one single environment? Like if I have
Two carbons on one side and two carbons, or one carbon on each side. 3 carbon.
Okay, so with 3 carbon atoms, you're going to get a single peak, right? Is there any other ketone that will have a single peak?
If you add one more carbon to each sides.
Like if I do this, right?
Yeah.
Like, will it have a single peak? Or not? How many? No, it won't. The CH3 and the CH3 have one environment.
Yeah, the environments will change. Yes.
Okay, so you're not going to have a single peak. So ketone is fine. I mean, ketone is fine because propanone. This one is wrong. So this is probably going to be this one because it gives you a single peak. And what type of alcohol is it made from? It's going to be made from a secondary alcohol. So that means there would be 3 H's, right? The 3 H's here as well. And the middle part would be H and OH, right? So is this spectrum matching this one? The CH3s will have one peak. The H will have another peak and the OH will have another peak. So what about, how many splitting for this CH3 peak over here? Singlet, doublet, triplet, what? The neighboring carbon atom has how many H's?
Doublet.
So it's going to be a doublet, okay? So it's this one.
Yeah.
I mean, the big absorption is going to be because of these CH3s, right? And it's going to be a doublet. What about this one? What type of peak would this be?
Multiplex.
Multiplet.
So this one is, and this OH is going to be a singlet. So you got a doublet, you got a multiplet, you got a singlet as well, right? And the height is kind of in the same ratio. Like these two are small because there's only one hydrogen, and this one is big because the doublet, lots of hydrogen protons are absorbing that. So it's probably going to be this molecule over here. And you can even look at the NMR spectrum. Remember too, it's the CH3 is right next to acetyl bond O. That's when you get something at 2. We just did that in the previous question. Is that clear?
Yes, sir.
So Y is, just make sure, go through the marking scheme as well to see how because we're not writing down the answer. They'll be breaking this down, but it's pretty much, I mean, that's the analysis. That's what you're going to do.
Sir, can you also send this worksheet on the group?
Okay, I'm going to send this. Try attempting this one. Okay, this one is, they've given you the MM+1 ratio, so you can figure out the number of carbon atoms. The number of hydrogens are 4, 1, that's 7 hydrogens, right? And I think, did they tell us? I said they didn't tell us the oxygens as well. That's oxygen is given as Z, so you would have to deduce the oxygens yourself. So I'm sending this in the group, and you can have a go at this one. So let's get in tomorrow then. Okay.
Okay, thank you.
Okay.
Lapis, sir.
Take care. Hafiz.